The European Council for Nuclear Research is making groundbreaking discoveries that it is trying to hide from society. Recently they've unearthed findings so striking from the Large Hadron Collider that they hint at the possibility of alien life in another dimension. This revelation has sparked a global conversation with experts fiercely debating what this could mean for our understanding of the universe. Could this sensitive information indicate that we are on the verge of understanding phenomena that were once considered beyond our reach? Let's explore the darker, more shocking implications of what lies beyond at the forefront of scientific exploration. The European Council for Nuclear Research, commonly known as the European Council for Nuclear Research, stands out for its pioneering work in the realm of particle physics. This renowned research hub recently made a startling announcement from its famous Large Hadron Collider, revealing a discovery so unusual that it could radically alter our understanding of the universe. The European Council for Nuclear Research researchers have stumbled upon findings suggesting the possible existence of alien life forms in a parallel dimension. This provocative idea has ignited a wave of excitement and sparked vigorous debates among scientific experts across the globe. It has been a hub of high-risk, high-reward experiments since it was founded in the mid-1950s. It has consistently been in the spotlight not only for its scientific breakthroughs but also for stirring public outrage at the European Council for Nuclear Research over potentially dangerous experiments that could create black holes, tear gaps in the fabric of reality, and pose other substantial risks. Among its most notable and debated achievements is the construction of the Large Hadron Collider, the world's largest and most powerful particle accelerator. Operational since September 10, 2008, the Large Hadron Collider is the latest major addition to the European Council for Nuclear Research's complex of accelerators. It features a loop of superconducting magnets that extend over approximately 16 miles and a series of devices that boost the particles' energy levels as they hurtle around the loop. The construction of this colossal scientific instrument cost over $4.5 billion, however many argue that the investment has paid off handsomely, as the Large Hadron Collider has led to some of the most important scientific discoveries of recent decades, including detecting the Higgs boson and numerous other particles previously unknown to science. The Large Hadron Collider at the European Council for Nuclear Research is an enormous machine, a marvel of modern science capable of accelerating subatomic particles to speeds just shy of the speed of light. As these particles zoom around its approximately 16-mile loop, they complete over 11,000 circuits each second, pushed to incredible velocities by a sequence of incredibly strong electromagnets. These magnets create a magnetic field inside the accelerator that is almost 1,000 times stronger than the natural magnetic field surrounding the Earth. There are concerns about the potential impacts of such a powerful magnetic field on the electronics nearby and the Earth's magnetic field itself. As particles within the Large Hadron Collider reach their peak speeds nearly equal to the speed of light, they are directed to collide with each other head-on. This collision results in a spectacular burst of energy and a spray of new particles which scatter in all directions. Most of these particles exist only briefly, decaying within fractions of a second. By varying the types of particles that are made to collide, scientists can explore and discover previously unknown particles amid the chaotic aftermath of these collisions. To capture and analyze the results of these particle collisions, the Large Hadron Collider is equipped with highly sophisticated and sensitive detectors placed around the collision sites. These detectors gather vast amounts of data from each collision, precisely recording everything. The data collected is immense, accumulating rapidly and requiring extensive time and resources to sift through. Each year, the experiments at the Large Hadron Collider generate more than 15 petabytes of raw data. The Large Hadron Collider has developed extensive storage systems to manage and store this data. In 2017, a significant achievement was reached when more than 200 petabytes of data were permanently stored in the Large Hadron Collider's tape libraries. To put the volume of this data into context, consider that 1 petabyte alone is equivalent to about 250,000 movies. The sheer scale of data produced by the Large Hadron Collider is staggering, encapsulating a wealth of information that holds the keys to unlocking the mysteries of the universe. This data, when meticulously analyzed, allows researchers to peer deeper into the fabric of reality, testing the limits of our understanding of physics and the universe. In the vast sea of data collected by the Large Hadron Collider, scientists are meticulously searching for clues that could unravel new mysteries of the universe. One particular focus of their investigation is a unique type of subatomic particle known as a quark. Quarks are the very foundation of all matter, existing in several distinct types or flavors, as physicists like to call them. Each flavor of quark behaves differently, but they are all crucial for forming the protons and neutrons that make up the atoms in everything around us. Among these flavors, some are incredibly unstable, quickly transforming into other types of particles almost immediately after their creation. One such unstable quark is the beauty quark, known for its exceptionally short lifespan, lasting just 1 2/trillionths of a second. What caught the scientists' attention was an unusual pattern in how these beauty quarks decay. Typically, according to the standard model of particle physics, when a beauty quark decays, it is influenced by a force known as the weak force and transforms into lighter particles called leptons. The expected outcome is an equal chance of turning into one of two types of leptons, either an electron or a muon. However, the recent findings from the Large Hadron Collider have shown something unexpected. The data indicates that when beauty quarks decay, they are turning into muons about 70% of the time, rather than splitting the chances evenly between muons and electrons. This significant deviation from the expected 50-50th split suggests that something unusual is happening, something that the current theories in physics can't fully explain. This anomaly has sparked intense interest and debate among physicists. The observed disparity suggests that a previously unknown particle could influence the decay process, or perhaps it points to a new kind of physical phenomenon entirely. Such a discovery would be groundbreaking, indicating that our current understanding of the fundamental forces and particles might need revising. Researchers are now probing deeper into this data, looking to confirm these findings and understand the implications fully. If this turns out to be true, it could mean the beginning of a new era in physics, with the potential to uncover new forces or particles that could fundamentally alter our understanding of the universe's workings. After a startling discovery, a deeper mystery emerges, suggesting there are forces out there that we've never seen before. Z', the particle that will rewrite physics, is the discovery of a new force-carrying particle tentatively named Z', which could revolutionize our understanding of physics by potentially expanding the current standard model, which is the framework that explains the fundamental forces and particles that make up our universe. This model has been remarkably successful in detailing three fundamental forces: electromagnetic strong and weak forces, but it doesn't yet account for gravity or explain dark matter, which is thought to make up a significant portion of the universe's mass. The possibility of new physics introduced by Z' comes from recent observations that didn't align with existing predictions. Such anomalies are not unheard of, given the vast amounts of data generated by experiments like those conducted at the Large Hadron Collider. Still, the specific deviations observed recently have captured the focused interest of the scientific community. These findings suggest the potential existence of a particle that behaves differently than anything we currently understand, interacting in unexpected ways with known particles like electrons and muons. This novel particle could be the key to unlocking many of the universe's long-standing mysteries. For instance, discovering a new fundamental force could shed light on the elusive nature of dark matter and further clarify the role of the Higgs boson in the makeup of the universe. More broadly, it could lead to a more complete and unified theory of physics, which has been a central goal in the field for over a century. The implications of such a discovery are profound, offering answers to complex questions that have puzzled scientists for decades. While the suspected interactions of the Z' particle with other standard model particles remain largely speculative at this point, the pursuit of understanding it is a thrilling prospect. It represents a potential paradigm shift in physics, akin to the major breakthroughs of the past, but unique in its promise to bridge gaps in our current theories. The excitement in the scientific community is palpable as researchers worldwide work to confirm the existence of Z' and explore its implications. If confirmed, this discovery would not only redefine our fundamental understanding of particle physics, but also pave the way for new technologies and insights into the very fabric of the universe. Elon Musk has highlighted that the European Council for Nuclear Research constructed the most enormous and powerful particle collider ever seen in human history, known as the Large Hadron Collider, over a decade from 1998 to 2008. This monumental project was a collaborative effort involving over 10,000 scientists and hundreds of universities, research institutions, and laboratories from more than 100 countries worldwide. The Large Hadron Collider is strategically positioned within a massive, approximately 16-mile-long tunnel that runs beneath the border area between France and Switzerland, close to Geneva, buried about 574 feet beneath the Earth's surface. The construction and operation of the Large Hadron Collider marked a significant milestone in the field of particle physics. It first made headlines when it recorded a collision of protons at an unprecedented energy level of 3.5 tera-electronvolts per beam, shattering the previous world record by fourfold. Later enhancements to the collider allowed it to reach even greater energy levels, up to 6.5 tera-electronvolts per beam. These advancements have made the Large Hadron Collider particularly adept at handling proton beam collisions and have equipped it to accelerate lead ion beams as well. The Large Hadron Collider is not just about achieving high energy levels, though. It also serves as a scientific instrument that has unlocked new frontiers in our understanding of particle physics. Most notably, its experiments were responsible for confirming the long-hypothesized existence of the Higgs boson particle, a discovery that brought the European Council for Nuclear Research into the global spotlight and helped clarify the mechanism by which other particles acquire mass. However, despite these triumphs, the collider has also been the source of heated controversy and debate. Critics have raised concerns about the potential dangers of operating such a powerful machine, citing fears of unforeseen consequences such as the creation of miniature black holes or the opening of rips in space-time. These concerns have led to legal challenges in courts across various nations. But for many in the scientific community, the potential risks are far outweighed by the promise of transformative knowledge that the Large Hadron Collider could bring. Some believe that the insights gained from the collider's experiments may eventually lead to a unified theory of physics, reconciling the currently incompatible theories of quantum mechanics and general relativity, while others hold out hope that this machine might finally uncover the elusive nature of dark matter or the force of gravity. This monumental collider has achieved multiple scientific milestones over the years, including its groundbreaking discovery of the Higgs boson. In addition, through several years of experimentation, the European Council for Nuclear Research has identified an array of particles that were previously unknown. But beyond these discoveries, the Large Hadron Collider's most significant impact could be its potential to unlock the ultimate secrets of the universe, unveiling realities we've yet to even imagine. As the Large Hadron Collider continues to operate and its detectors gather increasing amounts of data from particle collisions, scientists anticipate further significant discoveries. These new findings could revolutionize our understanding of the universe, from the tiniest subatomic particles to the grandest cosmic phenomena, altering how we think about everything from the fabric of spacetime to the nature of consciousness itself. The work at the Large Hadron Collider continues to fascinate, terrify, and inspire people worldwide as it pushes the limits of our understanding of the universe.